Let's try some numerical problems, especially related to sampling and quantization. Let's say we have the message signal given by a sine 2 by fct plus theta, where amplitude is a and fc is the frequency of this. So you may be asked, first of all, very simple question. Suppose compute a Nyquist sampling rate. So you know that fs sampling rate has to be greater than or equal to 2fc. Okay, so the minimum Nyquist sampling rate is 2fc. So whatever be the numerical value of fc, we can compute. Now the important thing is, suppose we have to quantize this such that each level is mapped to b bits. Okay, and so one of the questions we may be asked it is, we need to compute signal to noise quantization noise ratio. So signal to quantization noise ratio, which is also called SQNR. So we have done actually the ingredients. So what is SQNR? So signal to quantization noise ratio is given by the signal power, let's say PS, P signal, divided by P noise. Okay. So if the signal is given by this, we know that its power, P signal, is given by A square by 2. Okay, basically you can integrate this over the time period t and you will get it. And what is the quantization noise? So I repeat it here. If you remember, we are dividing, suppose the whole region into L quantization levels, and let's say the maximum amplitude which we represented by MP and minus MP. So the quantization interval was delta V equal to 2 MP by L. Then we took the quantization as a random variable, uniformly distributed between minus delta V by 2 to delta V by 2, and finally by taking the average 1 over delta V as a PDF, Q square dq from minus delta V by 2 to delta V by 2. What we got is quantization noise, which we call as PQ. We got it to be delta V square by 12. Okay. Now in the given problem, what is the maximum amplitude we can have? So A. What is the minimum? We can have minus A. So this A is our MP. Okay. So this minus A is minus MP. Fine. And since we need each level to map to be B bits, so L will be equal to 2 to the power B. So then what is the quantization noise? Delta V square by 12. So delta V is given by 2 MP by L square 1 by 12. So this is 2 times MP is given by A, right? So divide by L square 1 by 12. So we can write as 4 by 12 A square by L. Now L square. L is equal to 2 to the power B. So L square will be 2 to the power 2B. So this becomes 1 over 3 A square by 2 to the power 2B. So now what is then signal to quantization noise ratio? It is the signal power divided by the noise power, which is simply A square by 2 divided by A square by 3 times 2 to the power 2B. So A square gets cancelled up. So it becomes 3 by 2 2 to the power 2B. So in terms of number of bits, this is the signal to quantization noise ratio. And in dBs, what you can write is SQNR in dBs. It is 10 log to the base 10 of this quantity 3 by 2 2 to the power 2B. So which we can simplify like this. So by using the logarithmic relation is log of A by B is for log A minus log B, and similarly log of A to the power n is for n log A. So this becomes 10 log 3 by 2 plus and this becomes 20 log 2 to the base 10 B. So the computing these numerical values of logarithms we get The first part is equal to roughly 1.76 plus 6.02b. So this is the S signal to quantization noise ratio in dBs. When you are given that, you want to quantize it to B bit level. Okay. So then, suppose if we take some cases like suppose sampling frequency is suppose 1000 hertz, then you know how much the sampling frequency. So it is 2 times of. So this is suppose the frequency of signal 1000 hertz. So sampling frequency will be 2000 hertz. Let's say that A is equal to 1. Then we can compute the signal power. Let's say B is equal to suppose 6 bits. You want to map it to 6 bits. Then SQNR you can compute rigorously, and then finally you will get it. It is 1.76 plus 6.02 into 6, which is equal to 37.88 in dBs. Another quantity which usually we are interested in is in the bit rate. Okay, so what is bit rate? Suppose you are sampling at suppose the frequency is f and fc, and you are sampling at 2fc is your sampling frequency, and each level is mapped to b bits. So the bit rate becomes denoted by rb equal to 2fc times b. Okay, so this is the bit rate. And so accordingly you can solve. Suppose if you are demanded that the bit rate should be, let's say for example, fc is equal to 1000 hertz, and you want that bit rate should be, let's say 100, or we can say kilobits per second, then how many bits should be there? Okay, so let's see, we can solve it. So it is 2 times 1000 into b equal to 100 into 10 to the power 3. So you can see this that this and this gets cancelled, so b is equal to 50. So you need to map each level to 50 bits, for example. Similarly, b may be given to you and maybe ask you to find the frequency or the sampling frequency or the frequency of signal such that we are getting a particular bit rate. We can easily solve such problem. So that was a small video on solving some problems based on sampling and quantization, which we could not do in the class because of lack of time, but I think the short video will be very helpful. Thank you.